welcome to another episode of AI Research Today. I'm your host, Aaron, with Architect AI. We help businesses automatically build advanced enterprise-grade software solutions using our proprietary platform, Architect, which is an agentized system and unsurprisingly is related to the paper today that I've chosen to talk through. So for those who've joined the last few episodes, we went through GradMem, language model injectivity, and a few other things like that. Some of those papers were fairly mathy, I'll say. And the paper I've chosen today isn't particularly complex from a technical standpoint, but it is an interesting paper. So the paper itself is called OccuBench, Evaluating AI Agents on Real-World Professional Tasks via Language Environment Simulation. So the reason I chose this paper, one, because it was part of a research segment from another podcast I really enjoy, is the Last Week in AI podcast. So shout out for the paper recommendation. But the paper itself takes a unique approach to baselining and evaluating agentic systems. So agentic systems are the big buzz in industry now. I think it's sort of the next iteration of the AI revolution, which is really beyond just a chat interface. Can a generative model actually make decisions and drive value using connections via API? And in some case, some research organizations are looking through direct browser actions rather than relying on API availability for agentic integration. We've seen a lot of agentic use cases across industry. A lot of them focus on things like text to SQL. For example, like a call center we were working with, they had a large pile of structured data in a call center related to account and metadata, like how long has the customer been with us, what account level permissions they have, etc. And there's also unstructured data. And so you can't necessarily build a RAG directly on top of that. So it kind of becomes an agentic benchmark where an agent has to figure out where it should go look for the information first, then build up a potentially SQL query to pull information from the relevant database, and then populate that information back to the user. So there are a lot of agent benchmarks that exist. This paper certainly isn't the first one to propose a agentic benchmark. I've released some research papers, personal plug, benchmarking agent systems on the App World environment. So App Worlds is a benchmark that includes recreations of common software platforms like Spotify. I can't remember the others off the top of my head, but there's several other popular apps. Venmo, that was another one. So there's several popular apps that it sort of implemented dummy versions on, and the agents are given tasks like go into my Spotify list, find the 10 songs that were mentioned in the most recent email from my friend John. And it's a stateful environment. So there's a SQLite database. Again, I'm speaking about the App World just to give a little bit of context here. So the App World benchmark has this stateful SQLite database. So when you're operating in the database, those operations are logged as database transactions. And then when an agent says that it's completed a task, some unit tests are run on the database to see if the final state of the database matches the expected final state of the task. So in this case, getting songs mentioned in an email. So the agent would need to understand there are multiple apps to interact with: Gmail, Spotify. It would need to go through the documentation, request tokens, etc. So it can be a fairly complex multi-step environment. But most of the benchmarks for agent tests are related to things like that, or navigating a 3D room, or website interactions. But this paper decides to look at industry categories. So these are more high value agentic tasks, and also higher risk tasks. So some examples they cite in the paper are: can an agent triage patients in an emergency department? Can an agent manage a nuclear reactor safety alert, or control greenhouse irrigation based on sensor data? And so the paper itself is called OccuBench, Evaluating AI Agents on Real-World Professional Tasks via Language Environment Simulation. So the key is the language environment simulation. That's what I thought was particularly interesting about this paper. So rather than setting up a stateful, deterministic environment where the agent has to come in and run some queries and make some API calls and get some results, they actually use sort of an adversarial environment where they have one AI functioning as the test environment, excuse me, and another AI that's actually making the API calls into this environment. So they call out the professional domains where AI is most needed, things like healthcare, finance, legal, manufacturing, logistics, government, energy, are bound to enterprise systems that have no public APIs or access and have irreversible real-world consequences. So obviously the nuclear reactor example has some irreversible real-world consequences if things are messed up. And there's also a lot of prohibitive scaling costs. And another thing they add in to this benchmark that's interesting is non-deterministic errors. So in a lot of environments, like the app world environment, for example, if you call the tool correctly, it will give you a correct response. But in the real world, this is not always the case. There could be rate limits that you hit, or some sort of connectivity issue, or silent failures, like data is returned in a different format. So there's sort of a lack of indemnipacy. I said that wrong. Whatever. Hopefully everyone knows what I mean. Across transactions. And so they simulate the environment itself by an LLM. So they set up a configuration where they define a variable C as a tuple of a system prompt, a tool schema, an initial state, and a state description. So the LLM itself becomes stateful with a dynamic and long-running system prompt. And the LLM itself can decide to randomly throw errors, and there's also operator control over, what sort of distribution of errors we want interjected during the execution of a task. So they set up multi-step decision-making process across 10 industry categories, and they run a series of models across these categories. These are both open and closed source, so they benchmark things like Claude, OpenAI, as well as some of the popular open source. Disclosure, this is put out by the Quinn team and the Chinese University of Hong Kong. So these are like the open source models that they focus on testing. So they basically test the open source Chinese models against the closed sourced US models, Gemini, Claude Opus, OpenAI, etc. And they find a few things. I'll just kind of breeze through their high-level results. So first of all, no single model dominates all industries. So they find that Gemini 3.0 leads in education and science, but struggles in healthcare. Claude Opus 4.6 excels in transportation and trails in commerce. And every model has blind spots that are invisible to single domain benchmarks. They also find that implicit faults are harder than explicit. So what this means is they group their errors into two categories. So explicit faults would be something like you get a 500 internal server error in the API response. This is an explicit fault because the system itself is telling you there's something wrong. Implicit is where the data set that's returned is incorrectly missing columns, or there's some sort of silent failure. And so it would be on the operator to be able to detect that that was, in fact, an erroneous return, even though the system providing the return is not telling the operator that. So obviously, those are going to be harder to detect for humans as well. So they state that average performance under implicit drops far more than explicit, which makes sense. And so this requires agents to independently detect data degradation. And they also find that scaling consistently improves performance. So across model families, the bigger the model, the better it performs across these different error modes. They find that GPT 5.2 is a 27.5% increase, going from none to extra high effort, where you're turning on the reasoning effort. And they also find that the simulators themselves, so when you're positioning the LLM as the simulator, that strong agents aren't necessarily strong simulators. So GPT 5.2 ranks first as an agent, but produces the worst environment simulation quality. So that's sort of a high-level overview of the introduction. They go through some related work, which really is sort of like what I was summarizing earlier regarding benchmarks. So there's a ton of benchmarks: software engineering bench, Work Arena, Android World, App World, like I mentioned. Interestingly, they don't mention App World that I was able to find in the paper, which I think is one of the more nicely constructed benchmarks out there. But regardless, there's a bunch of benchmarks, but they note that some of the limitations are environments require substantial engineering to construct and maintain. This is like App World, where you have to recreate entire applications and APIs. The tests are static, which again, every time I run a test on the App World benchmark, it's running the same test. Now, that could be a pro or a con, I think. Like if you're trying to compare models and every time you run against some benchmark, it's slightly different, then you have another axis of comparison you have to benchmark against, namely non-determinism. And they also note that domain coverage is limited. So existing benchmarks cover web browsing, code editing, desktop operations, and a handful of API domains. So this is, I think, a fair statement. So then their quest becomes to create benchmarks for these professional occupational tasks. There obviously is room, how closely is this realistically implementing a operational environment? Probably needs some domain expertise in there to validate that it is doing that correctly. But I think the approach is valuable, the language model as a simulator, to throw kind of a wrench in the gear. So in the third section of the paper, they formalize the language environment simulator. So they define this as a function f sub theta of S, A, and C. F sub theta is just your parameterized language model. ST is your system prompt. C is a tuple itself. So C is composed of the system prompt, which is the description of the environment and tool schema, initial state, and the state description. So this is something that's stateful. And then the action, input, action, and state. And then the AI, the LLM, provides a simulated observation and output state based on the input action. So you can imagine this if you're just going back and forth in a chat GPT window and you said, hey, pretend that you're a nurse, and it says, okay, an agent just, a patient just came in. What do you want to do? And then you type back, I want to take them back and check their heart rate. And then the language model thinks, ChatGPT thinks, and it says, okay, heart rate's really high. So that's kind of your new state. So it sort of goes through this back and forth simulation of state action, kind of couching it in the typical language of a Markov process or like a reinforcement learning sort of setup. But the language model simulator itself has this input configuration, which is a stateful description. It has the history, which is the history of all the action observation pairs. And it has a rubric verifier, which is verifying that certain things are handled correctly. So there is some sort of deterministic code verification going on here. And then it's communicating with the agentic LLM, which is the model being tested. They make a few arguments for why LLMs can serve as language environment simulators, LESs, as they call it. So one, these are the points they're making. They format priors, so pre-training on vast API documentation and tool call logs provides strong priors for generating well-formatted tool responses. AI is good at coding, right? And that's even evidencing itself in MCP best practices, where now the recommended guidance is, rather than just calling tools directly, write code in a sort of sandbox environment, and then that code executes against an MCP server. So a lot of these new trajectories and setups are taking advantage of the code writing abilities of LLMs, and that's something that is done here as well. LLMs are good at writing code, so they can provide a good structured JSON response that's simulated based on all these billions of code and APIs they were trained on during their pre-training. They obviously have a lot of domain knowledge as well, latent domain knowledge from pre-training just across the corpus of work that they're trained on. The system prompt can be maintained, and they're able to handle unexpected inputs more gracefully. Now, again, there are, of course, going to be some cons. Nothing's perfect. This is just my opinion, not stated in the paper, but I think, some cons are potential reproducibility and also how closely something actually ties to a real domain, a professional domain. I don't think, I didn't see in the paper where they clarify that it's benchmarked using SMEs from the different industries. So sort of just trusted that the AIs understand the domains they're being asked to construct clearly. Each evaluation satisfies 4 conditions in their setup. 1, it's solvable, so there's a valid solution. 2, it's verifiable, so there's a way to validate that the final state is correct. There's calibrated difficulty across different agents to distinguish agent capabilities, and there's structural variation across instances. So they designed 16 non-overlapping subtopics per scenario and construct a professional reference document for each, covering domain terminology, workflows, edge cases, and these documents form references that ground subsequent generations. Okay, let's discuss the fault injection a bit. So OccuBench evaluates agent robustness against controlled fault injection. So they categorize their faults into 4 categories. So E0 is clean, meaning there's no faults. If you make an API call, it works if you call it correctly. E1 is you're injecting explicit faults. These are things like timeouts, internal server errors, refusal of connection, service unavailable errors, just kind of like typical JSON responses from the server being called, the simulated server, I should say. Implicit faults. These are things with no error signal, like truncated data, incomplete lists, null, empty fields that may appear superficially correct, but upon further investigation are in fact incorrect due to incompleteness or missingness. And then they have E3 category, which is mixed. So this is approximately half explicit errors and half implicit errors. So I'll use these terms E0, 1, 2, and 3 when we kind of discuss the results a bit. So let's see. The first result that they discuss is the E0 completion rate. So this is just the tried and true API does what we expect. No errors on the server side, simulated server side. So they benchmark GPT-5, Gemini, Claude, Quinn, DeepSeek, the Claude family, Kimi K 2.5, GLM5, MinMax, Minimax, and Sonnet 4. The highest scoring model in aggregate across all of the industry categories. So the industry categories for E0 benchmarked were agriculture, business, communications, education, health, industrials, public, science, technology, and transportation. So across all of these, GPT 5.2 performed best with a 79.6% successful completion rate, followed by Gemini 3 and then Claude Opus 4.6. The first open source model was Quinn 3.5 Plus with a 69.9%. Again, paper was written by the Quinn team. So this was the fourth model. Below that is DeepSeek, and then the remainder of the Claude family, and so on. So they the completion rate, the evaluation metrics, they quote in 2 forms: completion rate, robustness score. Completion rate being fraction of the 382 tasks where the agent's trajectory passes an automated verification against the rubric. And then the robustness score is basically looking at the resilience across different fault types. So let's see here. What do I want to discuss? Let's look here. So first, high-level insight. No single model dominates all industries. GPT 5.2 leads overall. With the high scores in agriculture, business, and industrial, and science. But its commerce score, 67, is far below Quinn. Gemini ranks second with the highest score in education. Opus 4.6 ranks third, shows the opposite pattern where it's strong in transportation and business, but weak in commerce, which is interesting. I wonder if that has to do with... I view Claude as a very... code-centric model. It's very good at quantitative tasks, and perhaps the industries it's shining in most are the ones that are more quantitative versus like education or communications. It may struggle with more, whereas more human-centric models like 5.2 maybe are better there. Again, that's just my speculation. Okay, so this one's interesting. So robustness, the completion rate across E1, 2, and 3 divided by E0, sort of like your completion rate across your error-prone tasks divided by your perfect tasks. Gemini 3 does the best with a 0.87. Runner-up Minimax, and then GPT 5.2 and GLM5. So the Gemini 3 has the highest scores pretty significantly um, across the errors. However, I will say for the error 1 rate, which is like the structured response error, Claude Opus 4.6 does pretty close to top, coming in 68 below Gemini 3's 73%. It also does pretty good in the mixed, but it seems to, or they all seem to struggle with the implicit error. GPT-5.2 does the best with the implicit errors. I think these are really useful results. Like if you're trying to design an agentic system and trying to figure out, maybe you have more of a situation where API failures are common, or maybe it's more frequent that you have implicit errors. These could be things like text to SQL, right? Like you have an agent that's querying a database, and that data may come out incomplete. You'd want an agent that's good at being able to detect that versus like if you're calling like App World, the Spotify API, and the Spotify app has an error, you'd want to be able to detect that. So, this chart could really help fine tune or give like a good place to fine tune your agent workflows. The unsurprising takeaway is that current agents struggle under adverse conditions. Even with just 2 fault events, the completion rates can drop by 15 to 20% across the board. It's usually 15 to 20% from below whatever the E0 rate was. So it's a pretty proportional fall across all the models. Another interesting ablation they do is generational improvements. So they look at across a family of models, like specifically they look at mixed faults. What's the completion rate? So the larger versus small model variants from each family outside of Claude 4.5, there's a 7% improvement for Claude 4.6 from small to large, like Sonnet to Opus. And Gemini as well, like Light to Pro, 11-point gap. So generational improvements for Claude, for example, go from 61 to 65 to 71. Sonnet has a large jump from V4 to V4.5. And they also do some ablations on reasoning efforts. So with low, medium, and high reasoning efforts, they look at perfect, so E0 industry baseline performance and a completion rate. And they see, like for GPT 5.2, going from none to low to medium to high to max high is almost a linear improvement in the agent performance. Interestingly, for Opus 4.6, going from low to medium is actually a decline in performance. So it goes from like 70 to 67. Now, this could, there's going to be some variance, but basically there's no large increase or decrease. It's almost flat. And even going to the max settings for reasoning only offers a minimal improvement in Opus 4.6. So maybe save the tokens. Anyways, that pretty much brings us to the end of the paper. I'll go ahead and wrap up here. I think I do like the idea of the agentic environment simulation. I think it could provide some interesting reinforcement learning opportunities. Like if you're to, let's say, focus on one particular industry and have it simulate an environment that's non-deterministic, so there's some sort of stochasticity in the environment, and you're rolling out trajectories and using like a PPO or whatever sort of update, it would be interesting to see how much you can improve at these tasks and what those improvements would be from, the final optimized trajectories versus the initial suboptimal trajectories. So I think I like the approach of using language models and environment simulator. I think there's some interesting research that could be spawned off of it. And the study itself does a pretty nice coverage sweep of different models and model families and reasoning ablations. Like I said in the beginning, it's not a mathy paper. You can give it a read and probably understand it the first time through. But that's not a dig on it. I think that it's very industry relevant. I think a lot of the results in this paper are really useful if you're in one of these industries and trying to build an agent system and trying to understand how different models could be expected to behave in different situations. This is a great place to get a start at answering that question, and also a great place to kind of come to hypothesize ways that you can improve a certain model. Like if you're in an industry, for example, health, and maybe you can't use a closed source model because you don't have control over the data, so you have to host an on-prem model. Well, you know which on-prem models are going to do best, and you also have a way to start doing some reinforcement learning tuning on these open source models to try and beat even the performance of what the closed source model would be. So a lot of cool directions you can take out of this. Again, the paper is called OccuBench, Evaluating AI Agents on Real-World Professional Tasks via Language Environment Simulation, out of the Quinn Alibaba team and Chinese University of Hong Kong. And that being said, I'll go ahead and wrap up the episode. Again, I'm Aaron, your host. You can email me at aaron.mcclendon@architectai.com. I'll include a link to the archive paper, as well as other relevant information in the episode description. So thanks for listening. Hope you have a great rest of your week.